Okay, today's lesson it has to do with Pascal's triangle. Now you've probably seen Pascal's triangle in different math classes posted up on the bulletin boards because it has lots and lots of sequences and patterns in it. Now our main purpose today with Pascal's triangle has to do with recreating it so that we can use it to expand binomials. So you'll see in a few moments how important this is in the sense of it is a time-saving uh, activity, if you want to look at it, math as being activity. So this is important. That's why there's stars here. Now Pascal's triangle, we're starting with the number 1. And so again, we have 1 and 1. So this is what we often call, this is the T1, this is T2 if you want to look at it that way. And then what I have here is the other terms are made using beautiful Pascal's triangle. So what happens is after that 1 and 1, all the straight down this way, we're going to have another 1. And we get this middle term by adding these other two terms together. So in this case, these two terms added together is 2. And then we finish with 1 again. And so then the pattern keeps repeating itself over and over again in that same kind of fashion. Now, obviously, the next one's going to have more terms to it. Again, I end up with 1. And to get the next term, I add the previous two terms together. So 1 plus 2 is 3. 2 plus 1 is 3. And I finish with 1. So you're starting hopefully to see kind of the pattern that's going on here. And the pattern just repeats itself forever and ever and ever, really, if you wanted to do it that long. So the next one would be, again, I start with 1. I get this middle term by adding these two terms together. I get the next term by adding them. Again, adding, and finish with a 1. Okay, we're going to do a few more lines dealing with Pascal's triangle because, as I said, you're going to need to be able to recreate it yourself. Okay, so again, if you notice, just like a pyramid triangle. So 1, these two numbers together, 5. These two numbers, 10. I have 10 again, 5, and 1. Right, so another one. It's not really that difficult after you know what the pattern is, and you have to remember what that pattern is as well so that you can recreate it. Obviously, I don't memorize these rows by any means. I just recreate the triangle to help me. So the next one is 1, 6, 15, 20, another 15, a 6 again, and a 1. And just for fun, and you're saying it's not fun, I'm going to actually put another one on here. And then we're going to look at it and admire it because math is meant to admire. So 1, we have 7, we have 21, we have 35. Oops, sorry about that. We have, oops, another 35. Sorry about that. Did the wrong one. Get out there. Oops. Oh, well, that wasn't what I wanted. 7, 21, 35, another 35, a 21, our 7, and our 1. And as I said, you could keep on repeating the pattern and it just keeps on going forever and ever and ever. So what's really going on here in the sense of what patterns can we find? Well, obviously we can see that if we look at, now I'm going to switch to my magic pen for a moment just so that it will disappear. So if I notice, obviously I'm going down by ones here. That's no big deal. But look at the next one if I go diagonally. It goes 1, 2, 3, 4, 5, 6, 7. Ooh, what about the next one? Well, I don't see quite as strong as pattern as the last one. However, if you examine it a little closer, you'll find that there is more patterns there. Now, what else can we find? Okay, so if we see ones and if we go diagonally, we can see other numbers. Um, what about if we chose and look at what we call triangles within triangles? We could do that as well. So if I look at, for instance, this part, um, you notice that we have double ones that are double in a few different places. One there, oops, sorry, and there. How often does that happen? Well, here obviously you can't have doubles. Here I have doubles, I don't have doubles. Here I have doubles, I don't have doubles. Here I have double numbers in the middle. Okay, so there is another pattern that you'll notice, and if you kept on looking, you would find lots and lots and lots of them. If you look at this one here, 7, 21, 35. What numbers go into all of those? Well, 7 goes into all of those ones. What if I look at this one, this row here? What goes in them? Well, obviously 5, right? 5 goes everywhere there. So there are infinite patterns if you want to just look at them to find them. Okay, so as I said, if you examine your textbook, it asks you to specifically look at different patterns. I'm not going to spend a whole lot of more time on that other than there are lots and lots of patterns that are useful in different situations. So the situation we're going to be looking at is its algebraic use, and the algebraic use as far as expanding binomials. Now, binomial is two terms. And obviously the first one, it's a plus b to the power of 1. And you're saying, well, that's not really expanding because there's really nothing there. Well, you're right in a sense, but let's take a look at expanding this one and expanding maybe in the next couple and then examining our Pascal's triangle to see if we can see a pattern that will help us expand more complicated ones. Well, obviously with this, that's just a plus b. We agree. And what's the coefficients in front of each one of those? We're just going to put that, it's the number 1. Okay, let's go and look at the next page, and this time let's expand this one. Okay, now this is a special pattern. It's a perfect square. So you know with a perfect square, it is this number squared, which is a squared, this times 2, which would be 2ab, and then finally the last number squared, which would be b squared. Now let's take a look at the coefficients that are in front of each one of those variables, because you're going to hopefully be able to see a nice lovely pattern eventually come out of this. So I have a 1, I have 2, and I have a number 1 here again. Now what I'm going to do, just so that we can, did that just bring out those? I just want the 1, 2. Okay, so I just want to take this. I'm going to group it and take it away. Oh, and I didn't group it. Group, group, copy, and I'm going to put it over here for a second. I'm going to paste it. And this one I'm just going to put back where we had it, so it hasn't changed it. Okay, so let's take a look at Pascal's triangle so far. Well, let's find a line that says 1, 2, and 1. Well, it's right there. And what about the one that I did down here with the ones? Well, 2 ones. So let's take it and let's move it up, and you'll notice that it's here. So it appears when a binomial is to the power of 1, these are the coefficients I get. When it was to the power of 2, these are the these are the 3 numbers that I got. So it would stand to reason, if this pattern is true, that when I expand this next one, I should have coefficients 1, 3, 3, and 1. So let's actually try that and see what we get. Okay, so this means there's 3 brackets that are identical. So let's go first of all, and we're going to have, oops, that's way too thick. We're going to have the same as a plus b, and that gets multiplied by a plus b squared, okay, because there's there's three brackets that are same. Now we did a plus b squared up here, so that means that we can actually just put it in for here. So that would be a squared plus 2ab plus b squared, and now we're just going to expand it. Okay, so we end up with a cubed 2a squared b, then the a times the b squared, so that would be an a b squared. Okay, now we're going to take our next term, which is b, and multiply it. So it's going to be a squared b. Then it's going to be b squared here, so it's going to be plus 2ab squared. And then finally we end up with a b cubed. Now we're going to look for common like terms. And let's see, do we have any? Oh, I must have missed the plus sign here. So an a squared b. Okay, so we have an a squared b here and another a squared b here. And then this goes with this one. Okay, so if we match them up, so we have an a squared, a cubed plus 2 and 3, so we have plus a 3a squared b. And then our jagged line ones, we have another 3ab squared. And then we have our b cubed. And let's take a look. Remember, we were after, let's look at the coefficients. I'll write them here. Here's 1, 3, 3, 1. And if we look at Pascal's triangle, let's copy that one, go back over here. And if we paste it, you can see there it is right there, 1, 3, 3, 1. Okay, so Pascal's triangle is giving me the coefficients. Now, what about how do I figure out what's cubed, what's squared? Well, that's the next thing that if I go take a look at. So you can see that it works for the coefficients. So instead of it taking me this long to answer this question, I should be able to do in 2 steps. So first of all, what I'm going to do is I'm just going to take this last line that we created here, and I'm just going to group it just so it's grouped together. And I'm going to paste it. That's not what I wanted. Let's clone it. Okay, so let's take a closer look at it. Now what I'm going to do is I'm just in this part that I'm experimenting with, I'm going to show you what would happen if I added to my question a b. If I put a b here, obviously I can't put a b, so if I put a b to the 0, and if I put an a to the 0, because b to the 0 or a to 0 is 1. Now let's look at the actual numbers here as far as exponents. It goes 3, 2, 1, 0 for A. Look what happens to the B. It's like 0, 1, 2, 3. Okay. Now would that work up with this last one? Well, that would be B to the 0. Those are to 1. And this would be A to the 0. So it works here as well. So we're going to do some examples now with actual numbers, and you'll see hopefully that how well it does work.